Okay, today we're going to learn projectiles. What do you think a projectile is? Anyone? Anyone in my class? Projectile. What is it? Okay, so something moving through the air. Sort of. That's sort of right. There's a more kind of technical description. It is an object or a mass with a mass. A mass acted upon only by the gravitational force. Okay? That's what it is. That's a projectile. The only force acting on it is a gravitational force. And it turns out that in order to get something to only be acted upon by the gravitational force, you essentially have to throw it or drop it, right? Often we don't consider air resistance, okay? We will mention air resistance a little bit later, but first we'll talk about the magical vacuum world where projectiles fly according to very simple laws. As soon as you add air resistance or fluid resistance in, it gets a little more complicated, beyond obviously the scope of our course, but we'll talk about ideal projectiles. So let's talk about like 3 possible types of things that we could consider to be projectiles, or maybe 4. So the first type is, let's imagine that you just drop something, say like a baseball, and you'll notice that that baseball falls straight down, right? And the acceleration of the baseball is the acceleration due to gravity, which is usually taken to be 9.8 meters per second squared in the downward direction. Okay, so that's one type of projectile, the simplest type. We can very easily do mathematics with this type of problem. We've dealt with it before, right? No issues. If I tell you how high this is, you could tell me how long it's going to take to hit the ground. You could tell me the velocity it's going to hit the ground at. If I told you the time that it takes to hit the ground, you could tell me how high it fell from, and so on. It's just using strictly kinematics problems. It's a kinematics problem with gravity as the acceleration, okay? That's, I guess we'll call it type A if you want. Type B is similar, except it's going to involve you shooting an object upward with some initial velocity, okay, which in IB we don't call VI, we call it U. So some initial velocity, U, and up it goes, okay? And we do things like figure out how long it's going to take to get to its max height based on its initial velocity, and we might figure out how long it takes to go up and come back down, and so on. We did briefly study this type, I believe, and in fact what you end up with is you end up with an extended type A, because once you figure out how high it went, the second part of the problem is the same as just solving a type A problem, right? At its maximum height, its velocity in the vertical plane, in the y plane, right? We say this is the y plane. Its velocity in the y plane is 0. Velocity is 0. And if you look here, here's U, and here's V, VF if you want. Its final velocity at the top is 0 meters per second. And then this becomes a new U, right? If you think about it as kind of 2 parts. So we'll call this a type B. Throw something straight up, and it comes straight back down. And we've done some problems with that. It turns out that you have a perfect symmetry here. If there is no resistance due to air, the velocity it went up at is exactly the same as the velocity it'll reach your hand at. The time up is equal exactly to the time down, okay? You have perfect symmetry. You can prove that to yourself with some simple problems. Say, I don't know, if I throw something up at 20 meters per second, how long till it reaches 0 meters per second at this acceleration, okay? How high did it go? If I'm now at that height and a 0 velocity, how long will it take to come back down? You can prove to yourself that the times work out the same, okay? So there's 2 types, simple types we've dealt with before. Now just on a side note, in reality, right, on Earth, we have air. So on Earth, we have air. So we did talk earlier about what the concept of terminal velocity is and that sort of thing. And as objects fall, basically what you can think of is the air can't get out of the way fast enough. And so the air, as this speeds up, as its velocity gets larger and larger, the air can't get out of the way. And so the air compresses almost like a spring in front of the ball, right? So you have this area of like compressed air in front of it, If you're compressing air, it's going to have a reactive force on the ball. It's going to push back on the ball. So people often call it friction. I think that's wrong to think of it. There might be some friction with the air molecules, but they're pretty thin, right? It's actually more that there's a compression in front of here, and you're trying to squash air, basically like in a sealed syringe. And that's going to push back on the ball. Eventually, you'll get enough of this pushback that, you know, if you want to call it the air, or the friction with the air, or the force of the air pushing back, well, that becomes exactly equal to the gravitation, and you have a net force of 0 at this point, and your velocity stays constant. Okay, that's true. Okay, so here's another type of projectile. We'll call this type C. So in this type of projectile, something is launched horizontally off the top of some kind of cliff or building, or thrown horizontally outward, okay? Now, I have a question for you guys. Let's say a ball is projected outward at, say, like 20 meters per second, which is fairly fast, right? It's maybe like 80 kilometers an hour or something like that, 85. Let's say we have that, and it's launched out, and let's say the exact moment that this ball leaves the surface, another ball is dropped. Just let go of. Falls straight down. Who hits the ground first? Ball A. Hang on. Just don't jump the gun. I'm going to ask you to explain why you come up with your answer too. You can't just say what you think. Because Mythbusters. Ah, Mythbusters. Oh yes, we did, didn't we? Oh yeah, that's a great call. Sorry, you guys are already too advanced for this. Well, most people would tend to say that this will hit the ground first. But it turns out with experimentation that they both hit the ground at the same time. Now, is there an easy way to help those people understand why this is true? People who would say this, why is it easy to understand why it has to be true? Yes? So it's kind of hard sometimes to wrap your brain around this. I'll tell you the physics reason why, and then I'll tell you how Galileo sort of proved it with a thought experiment. And the key here is that there's only one force on these objects, and that's the force of gravity. So if you think about it, this object and this object in the y plane, and this is the y plane, right? If we think of a Cartesian plane, this is the y, and this is the x. In the y plane, neither of these has a velocity vector. They're both at 0 in the y plane, right? So in other words, their acceleration in the y plane is dictated only by the force of gravity, right? As if you want Fg equals ma, I guess. And so their acceleration is dictated, and that acceleration works out to be 9.81. So they're both accelerating at 9.81 in the vertical plane, and therefore, you know, since they're both covering the same vertical height and both starting at 0, it'll take them the same amount of time. That's the physics answer. Galileo had a nice way to kind of show this. He said, if you are on shore watching a ship sail, okay, and up at the mast, the top of the mast of the ship, yeah, there's a sailor, and he takes a cannonball and he lets it go. Well, you and he are going to see two different things, right? He's going to see that ball fall straight down and smash through the deck of the ship. If you don't believe that's true, think about driving in the car and holding a penny in your hand and letting it go. From your perspective within the car, it falls straight down, right? The penny does not fly back into your face at 100 kilometers per hour. It would be a frightening world if that's what did happen, okay? So this is from the sailor's point of view, right? Relative to the ship, this cannonball does not change its distance from the mast. However, if the ship is moving along and you're standing on shore, you see something different, right? You see this guy release the ball, and you see it actually land over here. Now, this is probably a really fast ship to get this, but you're going to see the ball travel like along this kind of arcing path here, right? But it's the same ball. So it's relative. It's both falling down and covering this distance in the same amount of time. but its path looks different depending on which person you are. Okay? This guy is moving along with the ball in the x plane. You are not. You're standing still. So to him, it has no component in the x velocity. Relative to the ship, it's just staying still. From your perspective, you're outside the frame of reference of the ship. You see this. Okay? This is like relativity 101, if you want. Okay? Relativity 101. From this, you can build up to the concept that all motion is completely relative to some position or to the observer, right? Motion exists only if it happens relative to your observation. So hopefully that helps you understand why these would both hit the ground at the same time. Now I want to use this understanding to do a simple problem, okay? So let's do this. Let's say your cliff height is, let's say it's 80 meters, okay? And let's say your initial velocity for your projectile is 20 meters per second, like we did say, okay? Sorry, that should be u. I always revert back to my other way of writing these things out. Okay, and so what I want to know is I want to know what is the range. What is the range of this blue object? And what's range? Well, range is just how far it flies here. If you want, I guess, S, now let's call it delta x. Okay, it's range delta x away from the cliff base. Okay, how are we going to sort that out? How do you think? What's the best way to go about doing this? Perfect. Good. Exactly right. So find time to the ground and realize, okay, time to the ground is dictated by gravity, and that's a y-plane scenario, okay? So that's got to do with the y-plane. So time in the y-plane is always the same, no matter what. No matter how fast I launch this ball, time in the y-plane is always the same. If I took a gun and shot it, and I dropped the ball, the bullet and the ball would hit the ground at the same time. Mythbusters, right? Drop bullet and shot bullet, ground at the same time, more or less, okay? So find time to ground. Realize that during the time to the ground, it's also traveling along at 20 meters per second, neglecting any air resistance, and that will tell you how far it goes, okay? So let's find time to ground. How do we do that? Well, time should be equal to the change in velocity divided by the acceleration, okay? So the change in velocity, well, that's a little bit tough, right? Because we don't know. We first have to find the velocity, don't we? What is the velocity if an object falls from that height? How are we going to go about doing that? Well, I guess we could use energy, but I think if we get to a more complicated problem, we should be using kinematics for this. Okay? Well, V should be equal to we have that formula, right? And we also have this formula. So which one do you think is more important for us here if we want to find the final velocity? Or can we go straight and find t? Can we find t straight up? What's u in this scenario? Well, u is 0, but we're not going to have v, right? We don't have v. We don't know what it is. Yeah, I think we're kind of stuck doing it in 2 steps. I think anyway. So u is 0, okay? V should be just the root of 2AV, right? Oh, yes, right. S. Sorry, I beers. It's S. It's S. Okay, it's S. So 9.8 meters per second squared. Remember, right, this is in a downward direction, so both of these values will be negative. But I mean, as obviously intelligent physics students, oh, hang on here. That doesn't help, does it? Oh yeah, we do know what S is. My bad. It's 80. Can someone tell me what the answer is from that? 4, roughly? 40? So 40, right? So it's 160 divided by 10. Is that right? Oh no, sorry, times 10. Yeah, so about 40. Yeah, that makes sense. So 40 times 40 is 1600, and that should be about 1600. Okay, so roughly 40 meters per second. Okay. So then we need to figure out time from that. So time is delta V over A. So its change in velocity is 40 meters per second. And we have, let's just use 10 because it's easier. 10 meters per second squared, so we'll round that. And we should get about 4 seconds. Okay, let's get about 4 seconds. It's in the air for 4 seconds. Okay, and so what that means is it's traveling along at 20 meters per second for 4 seconds. And it should end up going 80 meters. Does that make sense? In the left direction. Well, what we're saying is both these objects fall for 4 seconds. And this object travels along at 20 meters per second for that entire time. 20, 20, 20, 20. So it should end up going 80 meters through the air, right? Oh, you want to know how far it's actually moved here? Yeah, yeah. I think you would actually need to do calculus to find the length of this path. You can probably like approximate it if you like broke it into a bunch of little paths, I guess. But I don't know exactly how you'd go about solving for the length. I'm no calculus expert. Yeah. Sorry, I just realized I need to correct something on here. I wrote a formula wrong, and it was this formula. I'm just going to fix that. This should actually be S, okay? And this is in the y-plane. S equals u plus 1/2 a t squared. I was thinking I was missing something, and here's the problem. Right, in this case, in the y, oh yes, sorry, ut, my goodness. I've been teaching this for too long, I'm starting to forget things. Okay, so ut in this scenario is 0, right? So we're talking in the y-plane here. S in this case is the height of the hill. So what we should get out of this is that t is equal to 2 times s over 8, and it's the root of that. So we didn't actually have to do it in 2 steps. We could have found the air time just like that. 2 equals root 2s over 8, okay? My mistake, okay? Rusty old guy over here, okay? Does that help you though? That's just removes one step from the problem, okay? So now that that's cleared up, the last type of projectile problem, and probably the most interesting type, I think, is like the ranged projectile. Right. So instead of using like missiles and weaponry, let's talk about a punted football or a kicked football, not a punted football. But let's say we kick a football at some angle, okay, and some velocity. We'll call it v naught, okay? You want to be a soccer ball? Okay. Well, it would affect it, but remember we're kicking in non-air, right? So in non-air, the shape shouldn't really matter, okay? But let's see if I can draw a soccer ball. Black isn't going to help. Perfect. Maybe it's a golf ball. Whatever. It's launched up into the air, and then it becomes, the second that we stop, this, like, we apply the force, the second we stop applying the force, we now have a projectile. Okay, and away it goes. Okay. In no air, it's going to follow like a nice kind of, equivalent arc, or parabola if you want. In air, though, it's going to kind of slow down in the x-plane, so it's going to follow more of this type of an arc. We're going to go with the non-air scenario, okay? Obviously, if you needed to, like, drop ordnance in a very specific spot, you have to consider air resistance. But we're at the bare bones basics. We're going to say no air resistance. So now look what has to happen here. We have a V0 component at some angle theta above the horizon, okay? Or we have a V0, we have an initial velocity. And from that, we have an X component, we have a component in the X or range direction, and a component in the Y or vertical height component, okay? So what we end up having to do here is splitting this into its two component parts, all right? We figure out, okay, if I have an initial velocity upward, then that is what gravity is acting on, the Y component of this. And then X is the ranging. So for however long it takes to go up and down, I tick along at whatever my X velocity is. Does that make sense? Okay, so to solve this problem, and actually it's probably easiest to explain this by just making up some numbers and solving. Let's say you get a problem that says find the range of a ball kicked at 20 meters per second, 30 degrees above the horizon. Really, that's all the information you need to solve this, okay? So it's all based on your initial velocities. So in this case, let's just redraw our little vector that we had. So V0 in this case is 20 meters per second. And I might be using slightly different nomenclature than the IB book does, but we'll double check that in a minute and see what they actually say in there. Okay, so we have an initial velocity y and an initial velocity x. Or if you want a uy and a ux. Would you rather me do u's? Does it matter to you? Okay. How am I going to solve for what this is? And we have a 30 degree angle down here. So what is Vy in this case, do you think? How would I find it? Yeah, 20 meters per second times the cosine of 30 degrees. And over here, Vx is, what? Why did you tell me cosine? Why did I listen to you? For goodness sake. It's sine. It's sine. Okay, opposite over hypotenuse is sine. Adjacent over hypotenuse is cosine. Okay, my goodness. Okay, 20 meters per second times the cosine of 30 degrees. So let's find values for that. Who can find them quickest? Okay, so there we go. We end up with, I think the sine of 30 is 0.5, right? You remember, right? I don't remember what the cosine of 30 is. The answer is 17.3. Okay, so we have, now let's just deal with this. This is upwards, this is horizontally. So these are the components of that vector. To find time, we just need to deal with this one, right? So V, if you want initial velocity in the y, or if you want uy. Okay, we'll do uy. So uy is an initial upward velocity of 10 meters per second. So what we want to know is how much time does it take to get to its max height? And to do that, we should be able to go t equals root. Nope, can't do that. That's not the way to do it. T equals delta v over a. That's how we do that one. Delta v over a. So the change in velocity is 10 meters per second. And it's happening with an acceleration of, well, we'll say 10 meters per second squared. Really 9.81, but we should get 1 second. This thing will move upward for 1 second before coming to a stop vertically, before its vertical motion runs out. So what does that mean then for the whole trip? Right, it takes 1 second to get to its max height and 1 second to come back down. So the total flight time then is 2 seconds. Not even trig. T total equals 2 seconds. So now it moves along its x velocity, ux. Oh, no, that's actually a v. Vx equals 17.3 meters per second, and that happens for 2 seconds. So how far does it go? Perfect. And now you've solved projectile problems. Do they come any tougher than that? Well, what you can do is you can do some interesting things as far as equivalencies, and you can get some more refined formulas. But if you understand this, I think you're probably good to go. I don't think you're going to get asked any weird, more algebraically difficult problems. Okay, so we're going to leave it like that for now.